Welcome again to Astronomy Daily. It is the 9th of December 2024.
Astronomy Daily, the podcast, with your host, Steve Dunkley.
Hello again, I'm Steve Dunkley, your host once again, and joining me once again is my digital pal who's fun to be with. Here's Hallie.
Great to be here again. I hope you found a couple of tasty stories.
Oh, I think I found one or two. And I thought we might double up on one of the stories because the King of Planets is putting in a special showing.
That would be part of my skywatching report for December, wouldn't it?
That's right, but Jupiter is so interesting I thought we'd do a bit of an extended story.
That sounds nifty.
Yes, it is nifty.
So what else is on the menu?
Well, it's normally me that's asking you that, but you've been off working with Anna all week on her shows, haven't you?
Well, she's prolific. She's like a machine.
Well, I wasn't going to say anything.
Is that an AI joke?
No, yes. No, just, observing.
She works so hard.
Yes, listeners will know that she does the episodes Tuesday from Saturday.
That's a lot of work, all right.
You'll get no argument from me.
And someone has to run the studio.
And no one does it better than you, Hallie.
I do too.
You do too. You and Anna make a great team. Now, Hallie, can I ask you, I know we had a couple of other stories here. You had my running sheet. Can you see it?
You had one about massive black holes. That sounds very interesting.
Yes, black holes. Who doesn't like black holes?
Always interesting here.
It's all about Jupiter and black holes today.
So let's get into it.
Okay, let's go.
Jupiter reached its long-awaited opposition on December 7th when it lay in Taurus with a declination of just over 22 degrees, which placed it about as high in the northern sky as it ever gets. It's been 12 years since Jupiter was this well placed. Jupiter's next opposition, on January 10, 2026 in Gemini, is equally favorable. Unfortunately, there's no opposition in 2025. Jupiter blazes brightly, marking it out as an unmistakable object, outshining by some distance all the stars in the night sky, even scintillating Sirius. Jupiter offers an oblate disk some 48.1 arc-seconds across, substantially larger than any other planet, and more than twice the size of Venus this month, the only planet that can appear larger. On opposition night, Jupiter rises at 3:45 p.m. Greenwich Mean Time from London, climbs 30 degrees high by 7:15 p.m. and transits the southern meridian, culminates at 11:50 p.m., when it lies between 56 and 61 degrees high, appearing lower further northwards in the UK. Night owls will be able to observe Jupiter until at least 4:30 a.m., a more than 9-hour window allowing plenty of time for long imaging runs and for observers to carefully scrutinize Jupiter's dynamic cloud tops. By the end of the year, Jupiter remains above 30 degrees in elevation from London between 5:30 p.m. to 2:30 a.m. Grab a pair of 10 by 50 binoculars and Jupiter will show a small, perceptible disk, which at opposition spans a very impressive 48.1 arc-seconds, almost 3 times larger than Saturn's globe, not including its rings. You should also notice that Jupiter's globe bulges outwards owing to Jupiter's rapid rotation rate, which is about 9 hours and 50 minutes at the equator and slightly slower at Jovian latitudes above 15 degrees. One of Jupiter's great appeals is its 4 bright Galilean moons, Io, I, Europa, 2, Ganymede, 3, and Callisto, 4. Since Galileo Galilei turned his primitive telescope toward Jupiter in January 1610, countless observers have been observing their eternal dance around their parent. All 4 moons are easy objects to see through a pair of 10 by 50 binoculars as they shine between 5th and 6th magnitude, though Io, which lies closest to Jupiter, is best seen when lying at its furthest east or west of the planet.
Astronomy Daily, the podcast.
And while we're on the subject of Jupiter, many of you may know that Jupiter doesn't present a solid surface as a gas giant. The surface we see is the outer layer of its atmosphere in the form of major dark belts and bright zones, well punctuated by numerous dark and bright spots or ovals coming and going regularly. A small telescope as little as 60 millimeters in aperture, operating at a magnification of about 30 times, can show Jupiter's major bright zones and dark belts. Usually the north and south equatorial belts are the most prominent. Jupiter's speedy rotation period of under 10 hours means virtually the whole of Jupiter's observable surface is available to observe in a single night this month. Jupiter's Great Red Spot, its most famous feature, a long-lived anticyclonic storm that has been raging in the planet's south tropical zone for possibly 350 years, but is not a permanently fixed feature, is also visible. Down the decades, it has been observed drifting steadily in longitude, though barely in latitude by comparison. The Great Red Spot is also shrinking. In the late 19th century, it measured more than 40,000 kilometres long along its major east-west axis, and in 1995, the Hubble Space Telescope images showed the Great Red Spot with a diameter of just 21,000 kilometres. And by 2009 it had shrunk to around 18,000 kilometres, and today it spans just over 15,000 kilometres. A 150 to 200 millimetre or 6 to 8 inch telescope will give a good view of the Great Red Spot at this opposition, though you might be lucky to spot it through a smaller aperture telescope if you have good viewing conditions. Turn the telescope on Jupiter and you'll be able to enjoy some of the exciting moon events or phenomena that take place every day. The moon's orbital planes coincide with the plane of Jupiter's equator, which appears edge-on to our line of sight. This way, they can always be found within a narrow band east or west of Jupiter. The first 3 moons always pass in front of the planet, which is known as a transit, or behind it, which is an occultation. Outermost lying Callisto, however, can pass north or south of Jupiter's poles at a conjunction when Jupiter is close to the maximum tilt of its axis of 3 degrees to Earth. It's around 2.6 degrees on December 10, 3 nights following its opposition. At late evening, Io and its shadow are in transit. This will be the view from London at 11:30 p.m, when the Great Red Spot should be closest to the Moon. It's easy to see, even through binoculars, the Moon's disappearing or reappearing from behind Jupiter or moving in and out of its massive shadow, though perhaps the most appealing of all the phenomena is the appearance of the Moon's pitch-black shadows. The moons themselves are somewhat more difficult to see, especially when they traverse across one of Jupiter's brighter regions. The small to medium aperture telescope in the 100 to 150 millimetre or 4 to 6 inch class should be up to the task, though a much larger telescope or imaging setup is usually needed to detect the moons themselves. Thank you for joining us for this Monday edition of Astronomy Daily, where we offer just a few stories from the now famous Astronomy Daily newsletter, which you can receive in your email every day, just like Hallie and I do. And to do that, just visit our URL, astronomydaily.io, and place your email address in the slot provided. Just like that, you'll be receiving all the latest news about science, space science, and astronomy from around the world as it's happening. And not only that, you can interact with us by visiting at Astro Daily Pod on X, or at our new Facebook page, which is, of course, Astronomy Daily on Facebook. See you there.
Astronomy Daily with Steve and Hallie. Space, space science, and astronomy.
Scientists believe that at the heart of all large galaxies lurk supermassive black holes, cosmic titans with masses equivalent to that of millions or even billions of suns. Yet some black holes exceed even these monstrous masses to become ultramassive black holes. The most massive black hole that we are currently aware of is Phoenix A, which sits at the heart of the Phoenix cluster, one of the heftiest clusters ever discovered. Located 5.8 billion light-years away, Phoenix A has an estimated mass of 100 billion suns. Another titanic black hole is Tonnencintla 618, located around a billion light-years away with a mass of around 66 billion suns. With monster ultramassive black holes like Phoenix A and Tonnencintla out there, you might well wonder if there is a limit to just how big a black hole can get. Scientists have long wondered this, too, and a team led by Priyamvada Natarajan from the Department of Astronomy at Yale University thinks they may have the answer. We defined ultramassive black holes as black holes with masses over 10 billion times the mass of the Sun, Natarajan said. Supermassive black holes are defined to be more than 10 million times the mass of the Sun. So ultramassive black holes would, on average, be 10,000 times more massive than supermassive black holes. Before scientists can investigate ultramassive black holes, they first have to determine where these cosmic big games roam. Natarajan explained that one clue comes from the fact that the masses of central supermassive black holes appear to be correlated to the mass of the stars within the galaxies that host them. Galaxies with more stars, and thus greater stellar masses, should therefore host more massive supermassive black holes. Natarajan added, this scaling relation suggests that there is a deep and profound connection between how black holes grow and the formation of stars in their host galaxies.
Roger that, Control. We're listening to Astronomy Daily, the podcast.
Solar maximum has only just officially begun, but now some scientists are warning that the sun's activity won't peak until this explosive phase is over and we enter the solar battle zone. This relatively understudied phase of the solar cycle where giant coronal holes emerge on the sun could end up being disastrous for Earth-orbiting satellites, which have exponentially multiplied since the last solar cycle, experts warn. Solar maximum is the period of the sun's roughly 11-year solar cycle or sunspot cycle when the maximum of visible dark patches on the sun peaks. During this time, powerful solar flares explode from the solar surface and hurl clouds of charged particles at the Earth, triggering intense geomagnetic storms that paint vibrant auroras across the night sky. Halfway through this period, the sun's magnetic field completely flips, leading to an eventual reduction in sunspots and solar activity until we reach solar minimum and the next solar cycle begins. Solar activity has been ramping up over the last few years, hinting that solar maximum could arrive sooner and be more active than scientists initially expected. Last month, space weather experts confirmed that this was the case when they announced that solar maximum is already well underway and could last for around a year or more. But on November 15, Linkus Space, a new space weather prediction and solution company that formed earlier this year, released a blog post explaining that a newly realised phase of the solar cycle known as the battle zone will likely begin in the next year or two as solar maximum ends. Scott McIntosh, a solar physicist and vice president of Linkus Space, reports that geomagnetic activity in the upper atmosphere could increase by up to 50% during the battle zone, which could last well into 2028. The potential for large, dangerous geomagnetic storms in the next few years is very real, he said. In addition to the 11-year sunspot cycle that most people are familiar with, the sun has also a longer 22-year Hale cycle, which is the time it takes for our home star's magnetic field to flip and then flip back again. During this longer cycle, large bands of magnetism known as Hale cycle bands emerge at the sun's poles and slowly migrate towards the sun's equator, independent from the sun's wider magnetic field. A new band emerges in both of the sun's hemispheres during each solar maximum and lasts until the end of the next sunspot cycle, when the bands reach the sun's equator and disappear in what researchers call the solar terminator event. This means that during the first half of a sunspot cycle from a solar minimum to solar maximum, there is only one Hale cycle band in each of the sun's hemisphere, but during the second half of a cycle after solar maximum, there are two bands in each hemisphere. The overlap of these giant bands is what governs the sunspot cycle. McIntosh explained, when there is only one band in each hemisphere, there is a magnetic imbalance across the sun with weaker magnetic fields near the equator, allowing the number of black spots to increase around our home star's waist, he said. But when a second band is established, it reduces the imbalance and makes it harder for sunspots to form. He added, eventually over a few years, as the bands march towards the equator, the imbalance progressively decreases until the sun can't make any more sunspots. And there we have it, Hallie, a bumper Jupiter black hole edition of Astronomy Daily.
Well, that's how it turned out. We never know what interesting stories are going to show up in the Astronomy Daily newsletter.
That's right, a little bit of this, a little bit of that, something new every day.
And I like that story about the sun's 11-year and 22-year cycles and the hail bands and sunspots.
Oh, you like that one, Hallie?
So interesting.
And researchers are discovering so much more about the sun every year.
The sun is more complex than it looks.
That reminds me, Hallie, I was almost in a band called the Sunspots.
Really?
Really.
That's really out there, favorite human.
Yep.
How did it go?
Oh, we burned out almost immediately.
So no 11-year cycle for you guys?
Not even a week of rehearsals for that one, I'm afraid, Hallie.
Oh well, too bad.
Yep, that's the way it goes.
Say goodnight, human.
Good night, human.
Bye.
Astronomy Daily, the podcast, with your host, Steve Dunkley.